on my personal device, not in the cloud. All right, so persons are saying that I'm low, can't hear me. If you can't hear me, please let me know. Right. Can somebody tell me whether or not they can hear me, please?
Excuse me, sir, you're very low on my end. I'm not sure if it's just me alone or other students.
Well, my
Sir,
mic
I can hear you pretty fine. I don't know.
my mic is up at 91, close to 100%. I've actually changed the mic on my device last year because of the same issue. So I pretty know that I work on that end, but still sometimes there are glitches. All right. So one person said that you can hear me. Try and adjust your system, or probably one of the solution you can quickly do is log off and log back on quickly, because sometimes that resolves the situation, the issue. I find
Okay,
it
sir, I'm
happen
going to log off and log back on.
briefly, yeah. So quickly because I'm about to start now. All right.
Okay.
So right. So guys, so last week we had some interruption for especially for the Wednesday lecture. I think pretty much for the others we got by somehow. On Tuesday I had some challenges with the room. Um, And of course, yes, on Wednesday I changed the room. So I'm going back to schedule to get a room that I'm okay with. I think I found one, but I will confirm that early next week, the room that I'll be using for the tutorial. So I just make that announcement right here. Okay. I suspect it might be 47 B7. So but I will confirm that early next week. All right, so let's go ahead now. I'm recording, of course. So yes, we started by looking at dot position vectors last week, right? And I just want to recap now. So we'll be looking at unit vectors, position vectors, coordinate angles, right? And sometimes they call them directed angles, right? In 3D vectors represent a force vector along a line, right? So you should be able to find the angle between two vectors. Once they are between 180, 0 to 180, determine the projection of a line, right? They should be able to do all of these. And then, right, these activities over here is what some of those key things that you should be doing in the class. All right, so let me continue. Okay, so now so quickly, we already said that unit vector is a descriptor of a vector. It describes the line in terms of the direction that it is going, and it has a magnitude of 1, right? And we spoke about how do you find a unit vector. So once you have a vector and you divide it by its modulus, you get the unit vector. And it says it has a modulus of 1, it's dimensionless, it's point in the same direction along the original vector line. So if the vector is going to the positive, it is a positive unit vector in terms of some of the quantities. And if it's going to a negative, that depends on what the different quantities will have, the I, the j, and the k, that could also determine it. We reverse a vector by multiplying through by -1, and it actually goes the opposite direction. All right, so the unit vector is denoted by I for the x-axis, j for the y-axis, positive y, of course, and k. So if you look here, just remind yourself, and this is right-hand grip rule. So the thumb is always in the z, and then in this case, the I and the j is in the xy plane. So pretty much most of the problems that I will do, this might be the way the problem is depicted, where I expect the z, depends on the problem, to be up in the vertical, and the x and y is that plane down here, in the horizontal plane. And we say the unit vector is AXI plus AYJ plus AZK, meaning all these represents your position vector being now divided by your modulus of your vector. And how do you find the modulus of your vector? You square each quantity. You square AX square, AY square, AZ square. And then you take the root of that, which is showing you this is what you end up with down here. So whatever magnitude that is, you take it now and you divide each individual quantity. You divide the AX separately, AYJ, and then AZK. And you will get pretty much a descriptor of the line. All right. And similarly, we also find a direction or orientation of a vector by looking at these angles here. So this is alpha is pertaining to the x-axis, as you can see alpha here going to the vector. So the vector is some vector out there in space. So for the x-axis, positive x, alpha is donated here, positive x. Beta from the y goes directly to that vector, and gamma goes from the vertical to that vector. So you get all of those, right? Now, it doesn't necessarily have to be in the positive, it can be in the negative. So those quantities can be either a negative or a positive, and so it will determine the final answer, right? Some cases when you find the root, you may have a plus and minus. And typically how you know the correct one is to look at it. If you have a sketch, you look at it. Once it's not over 90, you know it's a small angle. And if it's over 90, it's gone into the between 0 to 180. So you know that possible it might be a negative, depending on the orientation of the vector. Right? So it's dependent on what you get. You may get two answers, one positive and one negative, and they'll give you the ratio may give you a positive and a negative if you take the root. Depends on the problem you're working, of course. So pretty much what we do in order to find each one, we says cos alpha is going to be equal to the ratio of whatever we get, meaning this would be a component of your position vector, the AX, divided by its modulus. And they are different. Here, AX is different from A. A is modulus. And similar for beta here. This is going to be the quantity from the unit vector, AY, which is a vector from the position vector, right? Meaning you're taking it out, it was from in Cartesian vector form. So this is in Cartesian vector form, right? And so this is the modulus dividing each quantity. So they're not the same. Please remember that. There's always a modulus dividing each quantity. And so if it depends on which axis you're dividing, if it's the X, you know you use this one. It is alpha. If it's the Y, you use beta, and what it said. And you take the cos inverse of each one, and you find your angle. So pretty much there's a trig identity also that works for these quantities here. So if you square the angle square plus is alpha square plus cos beta square plus cos gamma square, all equals to 1. So from this, there lead out, you'll have another, so the unit vector from this is similarly depicted here. So you can also remember this. This is quite helpful, right? And it's pretty much the same thing, but it's just depicted in terms of the cosine of the angle. And they are saying all of these things should give you 1. If you find this, you put the angle inside here and you square each one of them and take the root. You should get 1. I mean, unit vector magnitude is really 1. Right? So this is depicted here. And look, the bold A here is showing you that this is in vector form, Cartesian form. While the lower A here, it is not so looking bold, is really modulus. These are modulus underneath here. So it's not A divided by A, showing that it is 1. So 1 is vector, one is a vector quantity, and 1 is a scalar quantity where it is just a number. Right? So modulus value is just a number. Right, so the vector may be represented in terms of its magnitude, which is the modulus value, and the direction now is the angle. So it will tell you why, if it is I, that's part of the descriptor, and based on that, you can find the angle. So all of that is indicating direction. Right, so that's why it's a vector quantity. So pretty much, we see a problem here. Oh my. So yeah, this problem here. So it says two forces, F and G, sorry, apply to the hook. So you have a hook here, you have two forces, one going up here, one going here. So one is F, it has a magnitude clearly 100, and G has its magnitude what? 80. It's not on there. Right? Now X and Y are in the horizontal plane, while Z is in the vertical. So most probably you'll get, this is pretty much going to be the orientation. So you don't have to worry about labeling axis and all of that. Don't worry about that. Right? That's not part of the exam. And that's not part of the course in terms of, but you still must use your right angle rule, whether you need right, so you must know about your right angle rule, what it says. So look, so for this force here, we can clearly see that A is some force out in space. The fact that it's out in space, it will have a shadow. It will form a shadow in the, it will on the XY plane, it will form a shadow. So see it right here, there's a shadow right here. All right, so it's pretty much a shadow there on the XY plane. As a result of that, this is 90 degrees. And so you could go ahead using your cos of the, so it's going to be cos 60 times 100, and you would get what? F prime. We normally call this line F prime. Whatever your force you have, we'll call it prime. Just to show you that it is the one that is right there, right? On the horizontal plane. And so that becomes the, and now of course you see that there's another triangle down here that's being mapped, and it actually gives you the angle down here, 45. So that's now on the horizontal plane, where it's right angle, it's 90 degrees right here. All right? Pardon me, please, sorry about that. So pardon me for that, please. All right? Sorry about that. This is not a regular teaching time. Pardon me for that. All right. So this is the hypotenuse for the lower curve in the horizontal. So this becomes the hypotenuse for that smaller triangle. So you have a triangle like this. This one down there. This. So this is 45. And as I said, that is 90. So this will get whatever quantity, right? So we're gonna look at it quickly as it's done. Right. So you say you're gonna use your trig to do both, and you're gonna put them in Cartesian vector and then add them. So let's see, because the objective is to find them put them into Cartesian and to add them, find the resultant of the F2, add two vectors in Cartesian format. All right, so look on how it's done now. Trying to get rid of this zoom thing here, it's in my way. All right, I try to work with it. All right, yeah, so I hope I'm not okay. So here we go. So now we're going to resolve F into both horizontal component and vertical component. So the Fz clearly is the value that Z is, and it can be taken from this triangle right here. Right, as I drew before, this is 90 degrees. So this is going to be sine going up in that direction for the Z components. So see it there, 86. And for the horizontal one, it is 100 cos, as I told you before. So that becomes 50. So the lower triangle, this is 50, become the hypotenuse of that lower triangle. It is going this way, so it means in order to go from origin to this point here, you must go positive x, negative y. All right? So everybody see why is it negative y? I hope everybody see what is negative y, because you're going beyond where the positive y axis is. Anything beyond here, around this back here, is negative. All right, and so here you have f prime, the hypotenuse. Of course, we did that already. And then now, so fx value here is going to be a cos 45, while this one is going to be a sine, but this one is going to be a minus because it's actually going in the negative direction. All right, and so from this we can clearly write the f into Cartesian form, because we know the value of it in the x, we know it in the y, and we know it in the z. So and the Z, so you see it there, so you can actually look at the figure and write them. So this is 35.36 in the X. This is in the Y, this is in the Z. All right. And of course, the question is asked, how do you find the unit vector? Everybody should remember that you use Pythagoras, the modulus, and then you divide each quantity by the modulus of it, which you know what the modulus in this case is. It is clearly 100. So if you don't get 100 when you square all of that, then you're wrong. Wrong. All right, what about if you got it like you got two angles? So you got one angle where it says you're gonna resolve G now. So we're given alpha, and we're given alpha as 111. So between here and here is 111. That's the angle, that's alpha. And then beta would have been from the Y to that force, which is going to be beta. So beta is in this case 69.3. Now, if we go back to your trig identity, we have cos square alpha plus cos square beta plus cos square gamma equal 1. You can clearly put it in and then transpose for that for cos square gamma. And so this pretty much will give you all of this sum. Sum of this will give you this. You have this value, and you put that over. And of course, you see now you have, in this case, as I told you before, you have a plus and minus value, and you take the root. And so one value is small, one value is large. When you look at the figure, you can see that clearly it doesn't pass the horizontal plane. G is not in the horizontal plane, it is less than 90. So it is clearly 30 rather than 120. If it passed the XY plane and come down here, it obviously would be it would be going up to 180, so it would have been the greater one. So if G was down here, it would have certainly been the 120. All right, and so you have 30.2 for that. And so you can quickly now put it into Cartesian format because you actually have the angles, you can know what it is. So there we go. This is 80 now, which is this value. And if this now would give you the unit vector, so this part gives you the unit vector now. When you put in angle, it gives you the unit vector. And that gives you the unit vector there, give you the unit vector. When you multiply the force by its unit vector, it should give you the force into Cartesian. So here now into Cartesian, right? And you can certainly go ahead and find the modulus of G, right? Which is already what? 80. You go back and you should get 80. If you square each one, take the root. And so all we simply do now to find the resultant of F plus G is to add all the i's together, all the j's together, and all the k's together. And of course, you have to observe directly numbers, and that would have given you the resultant. So you would have had F and G together, right? F was what again? This here, all of these. And so you would have gone and had these values, all the i's together, all the j, k, and you get that pretty figure there. So this is the resultant force, and we pretty much find the magnitude by using Pythagoras theorem, right? All right. What about this one here? It says the screw eye is subjected to two forces. You must find the magnitude and the coordinate direction angle and the resultant force, right? So let's look quickly. So it says you must have a plan when you start your problem. Use the geometry and the trigonometry. So look, you have F1 and F2. Now, this one is clearly in the negative zone. It gone down. It's a big angle, the 120. So it's past the XY zone. It's gone down there, somewhere down in the negative Z direction. And of course, it will, based on that, it will have, of course, some values there. Now, we have F. What do we have for F? We have its magnitude, eh? But likewise, we have the some angles here, right, into the XY plane that it depicts in, right? And it depicts quite a bit here for both forces. So let's look at them individually. and determine. So you have to determine, you have to add F1 and F2. So you do know them, but the first objective you're going to do, you're going to look at all the angles and you're going to use that to convert these forces into Cartesian form. Right? So you know you need the unit vector of them, and then you put them in. And then from you get the unit vector and you find the resultant force, you can go ahead and find the unit vector of the resultant force. And you will know its magnitude of all of that. You can find, and then you just simply divide it and find these angles. So let's look at how it's done. So the first thing you do, you take one force at a time. If you take F1, you will see that the 300 force is the actual scalar value of the vector, and it gives you some direction in some here. So it tells you when it maps in the XY plane, right, wherever it drops, it is at 60 to the XY plane, 60 degrees. And so we can find Z, the first one. So it is going to be a sine 60 times 300, right? And you get a positive Z. Now this here, this is F1 prime. This line right here, which is going to be from your origin line, right? So this is going to be a, right, your F prime, F1 prime line, which is the hypotenuse of a triangle formed down here, right? So we know for this triangle that this angle is 45, right? And once it is 45, it means that the X and Y is going to have the same value. However, one is positive and one is negative. The X is negative because this value down here goes beyond the X. So X is positive over here. Once it goes beyond here, going into that direction, it is clearly going to be in the negative of X, negative axis. All right, so it's going to be in the negative. And then, so the Y is positive and the X. So the X you use sine and the Y you use cos. So here you go. So F prime is equals to, once you have that, you can find, so we found this, right? We're able to find this because this is cos here now. So here we have F prime is 200 cos 60, which is 150, this line right here, right? So we find that F prime line right here. And then now, the fact that we have the hypotenuse, we get the other two. So this is, so as I told you, X is minus and Y is positive, and they are the same values, right? Now we can write our the Cartesian of the F1 force. So we know that the Z is that value, the X is that value, and the Y is that value. And we simply put them in, right? All right, what about F2? Let's look at F2 values. F2 now, right? And if you have any question, please feel free. I'm not looking at the chat now, so you can go ahead and ask any question. All right, so I'm just recapping quickly. So I'll just go through. So F2, what did we do for F2? For F2, it is as a simple case. The force is down here. The X is represented by, so from the X, this is alpha, this is beta, and this 120 is gamma. So we have those. So you can just quickly put those in to your unit vector formula, and you multiply it by its scalar form, and immediately convert it to Cartesian vector form. And that, of course, represents Newton. If you were to go back and use Pythagoras and root it, you'll get back the 500. All right. So then now we simply had all the i's together, all the j together between F1 and F2, and we simply get this quantity here, which is resultant force. The fact that you have the Cartesian of the resultant force, you go back and you use Pythagoras on them, and you get the modulus of the, so you'll actually get the scalar value of the vector, which is 482. And so from that, once you have this and you take it and divide them individually, you will simply can find the cos inverse. Whatever you get, you do the cos inverse of whatever you get, and you will simply get the angles. All right, I think everybody understand that by now. All right, so we're jumping on back to vector directed along a line. So we already talked about briefly about position vector. So let's just recap it. So if a force is directed along some line, then we can represent the force vector in terms of what we call Cartesian coordinate by using unit vector and force magnitude. So pretty much similar to what I was saying before, but this is just putting it into perspective. So we can find the position vector of any line along a line, right? We can also find its unit vector, as I demonstrated before, and we can actually put a formula to it. So it says multiply the unit vector by the magnitude. So this what we're doing before. This is actually what we're saying. Now this is a bold F, and this is a scalar F, right? Time the unit vector. What will be the unit vector have? It will have all the component of the x, y, and the g and the k component of the unit vector, and so you will convert the scalar force to the vector formula. So this is a very useful formula, guys. Please make a note of this formula. And it is the same thing if you see it written this way. But you will not see it written in this book, by the way. Go back. You will not see it written like this, but this is actually what it is. So that's a modulus of F. It's a modulus value. All right. And so let's look at another problem here. So the 400-pound force along cable DA. So here we see 3 cables. We see the crane. The crane is holding up this metal sheet, whatever you want to call it. All right, where is it? You just jump over. So it says the force is along the line DA, and the force DA, so you have to find the force DA. So that means you're going from D to A. So you also look at that, Look at the labeling. D going to A, not A going to F. So look, the force is pointing from F to A. So you have to look keenly at those things in the Cartesian vector form. Now, clearly, this sheet here, this point here is your origin. And if you see clearly, this is positive X, positive Y, positive Z. So anything down here will be negative Z, negative X, negative Y, right? All of those directions. So that will be negative X, negative Y, right? And negative Z zone. So of course you see that XY plane is right there, right up top. The positive XY plane is in the horizontal. You have to find the position vector of that force, right? That line actually. You have to find the position vector of that line and the unit vector corresponding to it. And they say obtain the force vector as FDA equals to 400 pounds times the unit vector. So you have to convert this force here into Cartesian form, which everybody should know what to do by now. So simply, let's say here, so the force shown that when relating D to A, so remember we say you're going from D to A. So for D to A, you must go what? X, Y, and Z direction, right? So remember, so we'll have to go 2 feet in the X. So look where we say we go. We go 2 feet in the X, right? So you see it here? Let's look. Let's put that 0 here. So you go 2 feet in the X, which is this direction here. So you see it here? That is starting from your 0. So remember, you're at 0, you go 2 feet in the X. So there. Alright? And then it says minus 6F in the Y. Right? So it goes 6F in the Y. Positive Y, sorry. I don't know why they have this minus thing here. It's not minus, I don't know where this thing come from. Is that an error in the slide? Didn't see it before. Those you have to be careful, guys. Those are not saying minus because look, As far as I'm seeing, the x is positive and the y is positive. So you're going positive y. Can you see it now? See it now? Right? So you go positive y, and then in order to reach D now, you're going up what? You're going up, up, up in this way, right? Which you go right up the top in order to reach it. So I don't see it. See why the thing is written that way. I think there's a little error there. I don't know where that come from. Those are positive, guys. All right, and then let's check that. Let's check. Okay. Oh, I see what is happening. Let's look. I was looking back at the position vector itself. So yes, the position vector is actually pointing at they go negative. Let me clear that. Let me clear that. Let me see. Okay. Yeah, let me just clear that. Yeah. Yeah. So it's actually correct. Let me just go back and look at that. So what it is saying when you write the position vector, so look, one other thing you need to remember, guys, position vectors is a relative quantity. I'm trying to get back my writer. I've lost it. Well, so it's I don't think that is that it? Yeah. So look, so what we're actually saying to go from D to A is you go A and then D minus it. So in that case, it becomes minus, yeah. So let's try it again. So you go minus, yeah. And then this you go minus 6, yeah. So they're correct. So yeah, they're correct. So minus, yeah. Minus 6, yeah. Right. 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 And then you go up positive Z to reach that point, yeah. So right, because you would have this all of this to do. Right. So basically, those are the answers. All right, remember, let me just point out one of the ways that I said that when you're doing these problems, to bring out the ambiguity, just find the coordinates, please, quickly. So A would have been 0, 0, right, for A, and so the X is 0, Y is 0, and the Z is 14, right? And then for the B would have been what now? The X would have been what now? The X for B. What's the X for B, guys? Please tell me. What you see the X for B? I'm asking.
Or would it be 5?
Good. So it would be 5. Nice. And then Y would have been how much?
Six.
Is it positive 6 or negative 6?
Negative 6.
Okay, beautiful. Right, beautiful. Following. And then the Z would have been what now? What's the Z?
I'm not sure what up.
Can somebody else help her? Can somebody else help her, please? Because look, it B is in the XY plane. Remember, it's in the XY plane, so therefore, obviously, it has no Z component. It's actually at 0. But you see that? So it goes 5, and it goes positive 5 here, but it's no Z component, so it's 0. And similarly for C, let's check C. C is over here. What is it in the X? So it's obviously in the negative X. We're to double what now? 3 minus 3. And then now what would have been your Y? Anybody want to tell me what is Y? Somebody guess? What would have been
like negative 3.
Ah, beautiful, beautiful. And then now what would have been your Z? I guess somebody
0,
give me
sir.
okay.
0.
0 again, because look, C is also in the, so look, this is a Z. The XY plane is there. It doesn't cross over. This is negative Z. This is positive Z. This is the XY plane. It doesn't pass 0. So it stays within the horizontal. So it must be 0 for these two quantities. You got it now? Everybody get it now?
Yes, sir.
All right, great. So simply, it's still there. So once you get those guys, remember, and I remember I've always shown in the lecture that we go dA, which is called relative vectors, RA minus RD, and so you put your A here, and that's an easy way to do it. I see some persons write it in the horizontal, but guess what happened? You can, did we find D? Oh, we didn't put D down. Let me put D down. So tell me D. Tell me D. Give me D. What's the X? What's the X?
Positive
Positive
Positive.
what?
2.
Everybody agree? Who disagree with her? Why is it not 5 or 3?
Because if a 3 would go straight out to the end like with B, it's kind of in the middle.
Beautiful. So it's in the middle where they have this little fancy 2 right here. So showing that it come from the 0 to, so it actually right this little line there. All right. And then now for Y, what is Y? For D. From the 0. Remember where 0 is? So this is negative Y. And this is positive going that way.
6.
Beautiful. All right. And then now, what is your Z, guys? Where's your Z?
0.
Cross here. It doesn't cross here again. So it's obviously 0 again. So from that, we will go and we'll put 2, 6, 0. And so that gives you minus 2I minus 6J plus 4. What do I have 4? It's supposed to be 14, sorry. Yeah. I was wondering how I'm having that, yes. 14K. Right. And all of that is what? Is in Newton. Is in what? Pound force is unit. So that is the unit. So that's why we got those values up there. So yeah, those values are correct. Right. Correction there. Those values are.
Sir, isn't it in feet and not in pound?
It was what?
Isn't it in feet and not in pound?
No, well, look, the measurement for the different units are in feet, but the force is in pounds. You got it?
Oh, okay.
So
Yeah,
once you
understand,
see they start to talk about feet, it is in imperial measurement. So that means the force is obviously, if there's anything about force, they're going to start talk about pound. If you see the measurement is in meters, right? And right, once it's in meter, you know it's Newton. It is SI. So once it's FT, imperial measurement. So they don't combine both. So you want see Newton and imperial together. It's either one or the other. Right? Or they basically write them. So because this is a measurement, actually this is not pound, sorry. This is actually just a length, sorry. Let me just correct that. So I shouldn't put pound here. Yeah, sorry about that. I shouldn't put pound because it's not the force part that I'm writing, actually. I'm just writing the position vector of the line. So the position vector is really a distant. It's in Cartesian format. So let me, because you actually can know the distance, Can I know the distance of the line from that? Could I calculate the distance of the line? All right. Oh, that's taking me on. I'm trying to get, so where's my writer again? So this is really FT. So see it up there. So this is what we get. So you simply write the position vector, right? And so the distance, see it right in front of your face and nobody answer me. So you can get the distance by using Pythagoras, right? So they use a little half here, so which is really the same thing as putting the half over it, right? It's either one or the other, right? I probably would have just put the little hat over it because a lot of people say little 0.5 up there. Yeah, they can't relate to it. Or they probably should just use that one instead. All right, because that one is more relative. And so you take the root, there's either one or the other, right? And then, so the length of the line is 15.3, right? So you actually find the length of the line. Now that you find the length of the line, you can actually go ahead and find the unit vector. You don't even need the force to do it. You just go and find the unit vector, which is a descriptor of the line. And it is going to be written in the direction of the line. And so when you find the unit vector, this quantity would actually work out to give you your unit vector. Because what you have your position vector. So each one of the quantities will be divided by 15.36, each one, right? And so when you finish finding the unit vector, you multiply it by the scalar. And this is actually in the form F, your force, is equals to your modulus value of your force times the unit vector, which is dA, right, of dA. And so that is in that formula. So please get accustomed to writing that formula. So once you have a force along a line, you could go ahead. If the force is in scalar form, you can convert it to vector form. But what do you know? What is the connection? There's a unit vector in each line. And you need to be able to identify the unit vector. So in order to get the unit vector though, you have to first find the position vector. The position vectors are depicted by the actual points. So it's between A and D. Those are what we call, those are the coordinate points, and we write them in relative form. So dA, the relative form is RA minus RD depicted, right? And similarly, if it was RAD they wanted, you could just multiply 2 by minus and you get it. Or you simply go back and write RD minus RA, right? So that's the difference. You see them? This is known as relative vector, right? So it's not A minus D, but it's a reverse. You reverse the order and you find the position vector always, right? All right. So similarly, this other problem here. Let me see what time we have. See what well I'm doing with the time. Okay. So, all right, I'll be quickly. This is similar. You have two lines here, and let's say you have two forces acting on the pipe. They say they want the magnitude and the coordinate angle of resultant force. So similarly, what you'd simply do here, you're just going to find the position vector of the line. You get the unit vector from that. You multiply these quantity. You get the position vector in you convert the force now from scalar form to a Cartesian form with the IGA, and you do the same thing for each one. All right. So this is typically what you have here. So you look at each one, and you just simply find the position vector, right, of the line, right? And then you divide the position vector by its modulus, you get the unit vector, which is really depicted right here. So they just did one thing. However, over here is not simply just find it. There's angle here, so you have to use ratio of the sides to get them. So this is y, that is x. So you know, so the x is negative in this case, right? So x is negative, positive y for this one. So you have a 45 angle. The hypotenuse is 3f, and you break it down into components, you have that. And of course, the y would have been you have to look for what you want, right? For the A itself, the y would have been 0. Seem to be on the xy plane. However, this one have a value which is what? 4. So the x and y is 0, but this is what? So you use the same relative vector principle there, and this is what you would get. Those are the components there. Right, but these are actually giving you them, so you can just write them down from this. So you'll get, what is the x, what is the y, and you just write that value down there, right? And then this, but you can use the same principle. Identify this one first, that one first, always. Use the same relative vector. So to get your R, to get CA, you know that it is going to be A minus RC, right? So this is going to be those coordinate points you're using, right? So it's the coordinate points. And similarly, for this one, you find those points, you have this point, and you use the same relative vector. They wanted So that's our CA, and then it says CB. So CB, the relative vector of CB, right, would have been B minus C, right? Same thing. And you find them, you subtract them, you get them. When you get it, you find the modulus of it, divide it through, get the unit vector, and you simply go on now and multiply the A21 by it. So this would have been the position vector divided by its modulus, you get the unit vector. And you just simply multiply to get it. Simple. After you finish that, you are able now to add both components. You've had all the i's together. So you have these, add that one to this one, that one to this I to I, J to J, K to K, and you get this lovely resultant force. You take Pythagoras now, and you get its modulus of the resultant force. Once you take the modulus and divide back by these components here individually, you'll get the ratio, what the cos ratio equal to for each one, and you're simply finished. So that's ABC, if you understand the process. I'll skip that one, and I'll go quickly just to recap it here. So the dot product, right? The dot product now, is when you're trying to find the angle between any two vectors going in, they're coming from the same point, right? And they have an angle between them. So anytime you have two vectors coming from the same point, same origin, and you can find, once you find the angle between them, you can use the dot product, right? So you have A times B. Just remember that A and B are not just scalar value, but vector value. Notice how they are bold. Once you see they are in bold, they mean vector, right? It doesn't mean, come again. So vector, remind you, they are vector form, or what we call Cartesian form. These are modulus. So in some textbook, you will see that product is A dot B. Come on, writer. A dot B. What is it going on here? A dot B equals to the modulus of A, the modulus of B, because of the angle between it. So in some texts, you will see it written that way. These are vector form. Some people might put a little hat just to remind them. You don't have to put the hat once it's bolding, but we know that. Once you write that, we know that you're writing, right? So this is another form to write it. I probably would change this, but what you need to know, these are bold, these are modulus values. Once you recognize that, and this is always on the formula sheet in exam, right? And you see it there in Moodle, right up there. And the range of the angle is between 0 and 180. So the principle of the dot product, it's a scalar. So when you finish multiply these vector quantities, you must get a scalar value. Remember, this will also give you a scalar value, and this will give you a scalar value, right? And then now, they said the unit of the dot product will be the product of the unit of the A and B. So let's show you what they're talking about. So when you multiply them, one thing you need to remember, you go this times the first one. That's all. That give you, so and the I square is give you 1. See them here? I square times I square is 1. J now times this one is going to give you 1. So this is just for the J part. Those are 1. And for the I part, those are 1. But for the actually vectors, you'll get a numeric value. Right? Simple numeric value. Remember now. And then for this one, similarly. Right? So what we typically do, because these you saw, look, this is like binomial. So if you go I times any other quantity over here, like the J and the K, it's automatically 0. So we just do the first one. So it's just the I times the I alone. And similar for this second line is just the J times the J. And the next one is just A times A. So that's all you do. 3 steps. And you finish for that product. Right? Remember, cross product is different. For dot products, just the I, the similar quantity times themselves. And you finish with that line. Then you go to the next to the Y, and is J times J, you get that Y quantity. And for the Z quantity, you go K times K quantity. So you go with this line, everything there, times that part, and you get it. And we're gonna demonstrate it. All right, that is showing you the right hand grip rule, which is in the notes. So you see the big thumb is in the Z direction, and the X and Y are always in a plane together. All right, so you can put them in the XY plane. You could put them in the you could put them in vertical or horizontal plane. In where you go. So if Y is up, X and Y must be in the same plane. So that's the rule of thumb there. All right. So let's go a little bit further. So we already, am I going behind? Yeah. So it says here, you must be careful of the sign. What do they mean? Sometimes when you multiply them, if you have a negative and a positive, chances are it will be minus. Remember, directly numbers follow just the same. So don't think that everybody is going to be positive. All right. So that's pretty much it. And once you find this part and also multiply this the magnitude section of the modulus here, it is just this time these two numbers dividing each other, and the ratio of it, once it's below 1, you get a decimal, you take the cos inverse of it, right? And it's the range between 0 to 180. So it can happen between a straight line. You can find if you have a vector going here and here, obviously it's 180. So once it's a little bit less than 180, you use the principle to get the angle here. All right, what do we say about this now? The projection of the vector of a line. So what we're actually saying, if you have a line out there in space, so anytime you have two vectors, so you have one vector here, and you have another one here. So this may be a force. This may be a line or another vector, or a position vector there, but it is a vector. If I want to get a line parallel to this vector line here as a result of this guy, all I need to do for this line, once I have the unit vector of this line, I can multiply by this and I get a vector, I get a parallel vector to this line from this force. All right? So only thing I need is the unit vector of this line. I multiply it by this and I get a parallel one to this original line here. So that's what I do. All right? And similar, so that line, right? You could also get the perpendicular to that line, right? By reversing the order, meaning that, so look, if a right angle triangle, you would have done cos. So similarly, it is like having this force here. Once you take, the angle here to hit as your normal find components. Once you say this force times the cos of whatever angle there, similar. So if a force and the force times the cos of this angle, you similarly get the same. You get a component of it. So you get a line that is parallel to this line here, right? And so because that is the case, and similarly, you know that f times sine theta will give you a line that is 90 degrees to this existing line. You can simply reverse the process to get f if you don't know f. It depends on what you have. So the dot product is quite helpful. So you can determine the component of a vector parallel and perpendicular line using the dot product. How do you do that? So it's find the unit vector of the line here, which is this, and then you find the scalar projection of A along the line. So that is, so the A cos theta is another way to talk about it, is a projection onto a line. So if you have a line here and you want to project this force here onto this line, same thing we're saying, same language, you just use a cos, right? Or you could use the unit vector. So what it depicts here, it shows you that once you have the vector, or the force, and you multiply by so once you have the vector or the force, but the force, notice the force is in Cartesian form and the unit vector is in Cartesian form. The fact that it's in Cartesian form, what it tells you about these quantities? These quantities are just going to be scalar quantity adding. They are not going to be vectors anymore. They're just going to be 1 plus 2 plus 3. So you will get what? You will just simply get 6. And you get a scalar number. Because remember, I times I, you get a value. J times J, quantity. Whatever the A times the J quantity, you get a quantity. And similar with the K in terms of the set. Right? So that's what it simply say, and then you could just reverse the order to get the parallel line, the perpendicular line. So if needed, the projection can be written this way. So this is the projection is what? Parallel line. One line parallel to the original vector line by using the unit vector, right? So this is same unit vector. Find the model. So from step 2, this is it. So you have the parallel line times the unit vector, you get back the original parallel line, right? And then you can reverse the process. The scalar and vector form or the perpendicular component can easily be obtained by scalar. So if you want to get the 90 degree to that parallel line, what it means that you get the original vector minus, so you use Pythagoras theorem. So you would have had the 90 degree would be the square of the original force that is out there in space, right? Remember now you had gone ahead and you found a that from that, right? But you want this. And how you do it? Simply, it is Pythagoras. So in order to get this quantity here, your unknown here, you simply use Pythagoras. Not true? Same Pythagoras principle follows. Right? So if any day you want to do that, feel free, but it is noticed. That is a vector quantity, vector quantity, vector quantity. In that case, so that is vector while this is scalar quantities. It doesn't matter of rearranging. So we're actually saying the 90 degree component in Cartesian. So if you get the vector of this in 90 degree and the vector of that in parallel, when you add them, you get back the original vector. Principle is still alive. All right, any question there? All right, now, all right, I want to jump into this part here, right? Because I have to go to make sure I go through all of what is relevant. So let's look at this question here quickly. So you have this, what do you call it, So the force acting on the pole. So you have a pole here, and there's a force acting on it. They say the angle between the force vector. Where's the force vector? See it here? It is not in scalar form this time. It is in what? Cartesian form. We have a higher J and K. Now, they give us this pole here, and they give us some measurement. They said to you, the angle between the force vector and the pole, so they want this angle here. Come on, writer. I don't know why it's not writing. Hold on. They want the angle here. Right. And they said the magnitude of a projection of the force onto the OA. Onto O going to A. So you know it's in the direction. So they want this force is going to be projected to this line. How do we get to a line that is parallel to this OA line from this force? What did we say a while ago? Can somebody recap me? What did I say? To take this to get a vector that is parallel to O going to A, what did I do? What's the first thing you do? Or what the most important thing we need to find? Anybody?
Unit vector the line.
Okay, so your first thing you need to find the unit vector of the line O going to A. Once you find that, but first you need to find the what? What's the first thing you do after in order to find the unit vector?
Get the coordinates.
Well, you get the coordinates, but you need to find the next thing after you find the coordinates. Before you go to the unit vector.
Direction.
Well, you would have seen the direction. You need the orientation, it already tell you the orientation. It says going from O to A. So you're going from origin to A. You need the position vector. And so see it right here. Position vector is saying R going to A, which is actually going to be A minus O. So once you find A coordinate, you actually find it. In essence, in this case. Alright? So whatever coordinate is A. So let's identify A. Just before we look at the solution. Solution is around here. What is X for A? You want to tell me?
Only +2.
What's that?
+2.
Who see that it is positive? Who don't see that it is positive too? Who don't see that it is positive too, and why? So where is x? X is running along this part. So if you look across here, you try to say x is going to be, so look, this you see this line here is mapping, this is z. This is just pointing to z. X obviously is a line parallel to this line because this is x direction, not true? So you want to look for a line, you say 2 meters here. If this is dotting to this point, right to here, and it shows you that this is z. Right? So this must be the x value. Right? This is going to be what? Negative z. Okay, gone below the origin. So this is the origin. You see, this is the xy plane, now this is the x and this is the y plane. So that you have a horizontal plane, but it gone below. In the horizontal plane, x is 2, while y is 2 incidentally in this case. So this is y, and this is x. All right, so all of that distance there, and then that is z. And so it is going to be 2, and they're both positive, and then z now is going to be what? What is z? What is z, guys?
-1, sir.
-1, because it gone below the xy plane. Everybody understand that when it gone below the xy plane, so that is z, and this is the xy plane. So this is xy plane. This is negative z. So it gone below it. So it must be -2. And so you go ahead, you find your unit vector. All right, again, you find a position vector, unit vector. So a number of things you could use, but let's look at how this problem is depicted. So all of this, you see the direction. So first of all, you establish and you know the dot product. So you need the position vector of A, and you need the position vector of B. This is what. So what is A and what is B? In our instance, the position vector of OA is what we need to find. And then B now is going to be this other force up here. All of that. Right? So that is B, the component of B. Then you need to find the modulus of that vector, and you need the modulus of this position vector. Right? So you need all of that, and then you have cos of the angle between them. So let's look on how it's done. So you go and you find the position vector, which is that. Then you find the modulus, done. F now is that. You find the modulus of F. So you know your modulus value, which you're going to multiply those. And similarly, you're going to multiply your two vectors using the dot product principle. So we look at it now. So here's the first part. So see it up here, A times B and A times B. So the modulus. So is I times I. Remember that. What was our position vector here again? 1 second. Let me just carry it on with us. So we can relate to it while we're talking. So can I paste it here? The software doesn't give me the option to do that. All right, let's look at it around here. It doesn't give me the option. I was trying to paste it. Let me see if I can paste it. Control V. No, it doesn't work in this software here. No, it doesn't work here. It doesn't work here so at all. So see what we actually showing you, what I wanted to show you is that how to multiply them. Just trying to find it. Let me write back this. This is 2i plus, okay, let me just write that. So RA OA, sorry, is going to be 2i plus 2j minus 1k, right? And F was this. So F is 2i plus 4j plus 10k. So all we do is 2i times 2i. And what did I tell you? Say I squared does? I squared is 1. And similar, j squared is 1. K squared is 1. So those would drop out. Because they're 1. And so it is 2 times 2, while this is 4 times 2. Right? And then it is 10 times minus 1. So that is minus. So you will get 4 plus 8 minus 10. And that gives you the 2. So that's why we're saying that you have to be careful of the directed numbers. And then once you get that, you find the AB, which is the modulus times modulus. It was what? 2 times something, or 3 times something. 3 times 10 something? 10.95. Right? Once you get that, you just simply put it in. So this is 2 upon that, and you take the cos inverse of it. Right? And using the dot product, that is as simple as that. Nothing to it. Right? So see it all depicted there. Multiply, what else are they asking for here now? So you can get the unit vector of that. So that will be the unit vector of the line if you want. So, the problem not finished. That was fine in what again? Let me remind myself. That was fine in the angle between them. Okay. It went on, and what else the question had asked? The question said that they are to find the angle between them and the magnitude of a projection of a force. So it was doing projection of forces too. Trying to get back to where we are. So the projection here now, once the project this, you just need the unit vector of this line. So once we have the position vector, you need to get the unit vector, which is what is depicted up top. So there you have it up top. This is the unit vector, 2/3 I plus 2/3 J minus 1/3 K. Unit vector, done. You multiply the unit vector times this vector here, same principle like before. I times I, J times J, K times K, see them there? And guess what? This is now the parallel force to this line here, which is that, but this is a scalar form of the force. All right, cool. What else do they want now? They say that, so that is just showing you. So the angle that you found was that. Then you found the unit vector to this. That was the horizontal force. All right, and they say that like this is another approach given. You could use the projection of the force, scalar value of the force times the angle between it, and you would get this value right here, which is what they are showing you at the bottom here. So it's 10.95 times the cos of the angle. So you can use the angle because we found the angle, and you got about the pretty same value, nothing different. All right, and so that is it for that part. This is pretty much the same. All right, in interest of time, I'm not going to go through these. Pretty much the same. What I'm going to do is jump and recap now the tutorial. I'm just going to walk back through it briefly for those persons, and you can ask questions. So switch to your tutorial. Let me just come out of this. I'm going to discard all of that, and I'm going to open my tutorial now. Hold on. So I want a tutorial sheet. Here's a tutorial. Well, let's go back. All right. We want the tutorial. All right. So this is a tutorial sheet, guys. All right. So here we are. I use it. I went through one recently. Did I save that file? Probably didn't save it. Wow. Any questions so far, guys? Any clarity? We're all clear? Everybody good? I just see 16% out of our... Yes?
Yes, sir. I understand it very well.
All right, great. All right, I like that. Yeah, so look, I noticed that even though I'm taking the time out to do these sessions, I noticed that the attendance is really not anywhere. So I guess everybody kind of understand what is going on, even though we have had challenge since week. I'm hoping that that lecture theater situation, they told me that they resolve it. I'm going and check before class for those for our Wednesday class, and then, well, if it's not resolved, guys, I'm gonna go online for my lecture. I'm gonna tell you straight up until it is resolved, because I'm not going into it. Not another week. All right, not going there to be on cell phone. That's not ideal. All right, so this is it. I'm just gonna quickly recap this tutorial here. So stop me, feel free while I'm recapping. As I told you, I'm recapping. So I'm expecting that you will just flow with it as best as possible. Though I don't like when the software does that. Really give me a warm time when it does that. This is a really lovely software. All right. So this is a question. So the question says, this is a frame that they have there, right? What the question says. It says first you have to find the position vector of the rope AC, AB, AB. Right. So everybody by now should know when they said, but in this case here, they're actually trick. It's a little trick we have asked a question. They're saying, because what they really want you to do, they don't want to find AC, they want you to find CA first. They want you to find BA, right? So you find them, the first thing you go ahead and you find the coordinate points. After you have done that, then it is smooth sailing right there. So for this intent and purpose, I just ask person to at least tell me the points quickly. I'm gonna write it over here very quick. So just work with me. Give me A, right? Give me B, give me C, and I know you cannot give me D at this point. D is incomplete. So what is A, guys? Position the eye tweet. What is C? Hello.
So A is like 0 in the X position,
Mm-hmm.
0 and 35.
Oh, beautiful, because it's coming. Right.
Positive 35.
Right. Yeah, man. Right. And then now for B, how do you find B, please?
So you have to treat B like you're trying to find sin and cos. To be
Right,
like,
because they just didn't give the position this time. They want them for you to do some calculations. So you look and you see you have a right angle triangle here. All right, this is 50 is representing the hypotenuse for that side. Right, that is a shadow line for AB. It's like the shadow line of AB, right? So it's like AB prime. We always call them prime line. And that is the hypotenuse of that triangle down there, right angle triangle. And so for the X, it would have been 50 sine 30, but it of course in the negative zone. And for the Y, it would have been 50 cos, right? Because it lies adjacent to it. So that's why I know. And it is in the positive Y, right? And so you will find those, right? So X and then Y. So you'll have those components. And for the Z, you know it is 0 because it's in the XY plane. So you'll have those components immediately. So you could actually write, but they don't ask you for A going to B. They say it must point into A. So what they really want is this, reverse of AB, and which is really RBA. So it's RBA they really want it first. And so you'll have to write these points here. This will be minus 25. And this would have been some 43.3 something like that. And then this would be 0. And then C would have been, can somebody tell me C please quickly?
seems like 25, negative 30, and 0.
Negative 30 because it's in the negative side for the Y. Positive for X, because remember, see the big 0 here as the origin. And then this is 0 for that. Yeah. All right. And so once you have those, you should be able to find position vector A and B. And then it says also here to find the unit vector. So from the position vector, you write the unit vectors. All right. So pretty much that. Just a recap. All right. So basically RCA would have been really be minus 25 I plus 30J plus 35 K. And all of that is in feet, eh? Because it's a position, right? And then similarly, they wanted RBA, which is similarly going to be, or of course, it would have been A minus RB, relative vector. And then this one would have been RCA would really be A minus C. Right? So you'd have done those the long way. And for this one, the value would have been 25I plus 43.3 plus 0K. And all of that is feet again. Right. And then now all you need to do to find what the next stage of it they're asking for AB and AC, you just simply multiply minus 1 through all of these, because RCA is equal to the minus RAC, sorry. Let's erase that. So the first one, RAC, going the positive way now, would mean that is just a minus of RCA. So whatever you had before, you just multiply 2 by minus. Alright, 35. Alright, and that will give you a positive minus 35 I G I K. Alright, that is feet. And AB similarly would have been RAB equal to the minus of RBA, which is simpler, minus times BA, which is 25I plus 43.3. Multiply through that, you get minus 25I minus 43.3 J plus 0K. Right. Done. All right. So you get AB. Now that you have those, guys, and they're asking you for they're asking you to determine the resultant force of them. So in order to, so look, you have the position vector, you need to now find the unit vector. And the unit vector, you just use the modulus of each vector and divide each component. And so your unit vector of AC and unit vector of AB is simply putting each component upon its modulus. So this first one would have been 25I minus 30J minus 35K, and you divide by its modulus. Each one modulus would have been, I'm gonna give you the values quickly, in just of time, it's just 61. Let me see. AC would have been 52 point, it's a 444. Right, you divide it to get the unit vector. Similarly, you do the same thing to this one, minus 25I minus 43 J plus, is that 0? Yeah, did I have that right? That's one correct. That's AB. AB was what's the last component for AB? It's minus 35, no? How did I get? This is, hold on. I wrote something wrong. What was AB? AB was what was BA? It would have been 0 to did I write something wrong, guys? I'm just checking it. Was one of them 0? Just checking it quickly. I'm seeing AB as 0. Let me just check it. AB was supposed to be minus 35. Yeah, so this is minus 35. I think one is positive and one is minus. Yeah, I think this is minus 35. I think BA would have been incorrect. Let us check that. Yeah, so the vector would have been minus 35 for it. I don't know how I get 0 here for B, and B was 35. This will be 35. Yeah. All right, so I'm correcting that. What else do I need to correct? This one to 35. Yeah. Yeah. So there's no 0 on there. I'm just checking good. What was written as 0? Yeah. So none of them are actually 0. Yeah. Good. All right. So it's 35. No 0 there. And so this would have been AB is supposed to be 35. 35K.
Wait, sir, could you recheck RBA? Because I'm not sure that's right. Isn't it supposed to be?
RBA,
Yeah.
RBA, the reverse, it would have been minus RBA. Let me see. It would be RBA would have been minus. I have to go in a little fast here. This will be minus, and this will be positive 35. I was trying to write them down quickly, and then just in interest of time. So that would be so BA, and then we'd have reverse the process. So AB would be the positive of that, no? So all of those values would have been positive for AB. These would be positive, and I think 1 negative. Yeah. So this one will be minus. Yeah, that is the difference. So we would have reversed the process. We did them last week. I was just trying to write the values down. I have them here, just trying to find them quickly. And then AB was, so we simply put them up on each other. AB1 would have been 60. The modulus would have been 61.032. All right. So you can go back and check them. I'm just quickly jotting down some values that's supposed to be here. All right. So you can go back and check them. I'm saying it clearly. Yeah, there might be a sign issue there because I'm writing them quickly down. Just confirm that they're all right there. I don't want anything on this slide that is incorrect. Minus 35. So this is 35. And right. Yeah. Right. Yeah. So it means that these were minus. What was minus here? Yeah. This would have been minus. Right. Those would have been minus. And that's why we got them positive down here. Sign change when you multiply through them. All right, so you put the modulus behind them and you get the unit vector of them. Once you get the unit vector, you're gonna multiply each. So for AB, you multiply the unit vector of the line by the force. And you do that for both of them. All right. So we had gone through all the classes with this one, just reminding the process. So then now you employ the formula, which is F1 is equals to F times its unit vector in its line. All right? That's F1, right? F1 was F, right? And similarly, you do F2, right, times the modulus of it times the unit vector of A. This was what? CA? What was it again? It was AC. C. You say we're going from A to C. This is AC. All right? So all you do, multiply the unit vector of those lines. All right. So typically F1 would have been 350, right, times the unit vector 0.04096 I plus 0.7095 J minus 0.573, right, 5 K. So those will be unit vector, and they give you the force in the Cartesian format. that would typically be, so you should get 143.4 I plus 248 J, 3 J, and the next one would be 207 K, right? And that is all in pounds. So that is converting it to Cartesian. And then you do the same thing with F2. F2 was what? 400, right? Let me see if I wrote that one correct. Yeah. And then F2 would have been using the same formula, this formula here, times its unit vector of the line AC, because you're doing AC now. So this is F2, F2, UAC. Right, so the vector F2, so that would be, what's the unit vector for that one? It would be 0.4, 767 minus 0.571 J. And then the other one would be 0.6674. Okay, right. And then you multiply it, you get them. So they would have been 190.7 I. I will send you a slide doing the total tutorial straight where I actually go to the details of it. All right. But I'm really not going through all of it tonight. All right, so we did that. And all you do now to get the resultant, so the resultant that they wanted for just F1 and F2. Some people will call 1 plus 2, whatever you want to write. So F1 plus F2. So all you do, you link I, and you link J and J, and you link K and K, and you get one result for this, which is going to be 334.1 I plus 19.5 J minus 400, sorry, 467.7 K, right? So you get the resultant. And once you get the resultant, you apply Pythagoras and you can get what the resultant force magnitude is. I think it's about 500. 575.1 pounds. Right? All right. What else did they ask you to do? They said that here, after you get the position vector and unit vector and all that, you find it, you must find the angle of the angle, the coordinate angles. So the coordinate angles, which is in D, is expressed them in Cartesian. All right. So you find the resultant first, and you express them in Cartesian, which is this. Then E says the vector determine D in terms of magnitude and direction angle. Express the vectors in D in terms. So all you need to do now is take the magnitude of the force, divide each quantity to get the unit vector of this. So we're getting the unit vector of the resultant force, 1 plus 2. So it is going to be 34.1 I plus 19.5 J minus 467.7 K. And you take now the 575.16 and you get a beautiful unit vector. Did they work out unit vector? Let me just see. I'll just give it right there if they did or they did not. I don't think they work out the unit vector. You can work it out. I don't have the value for it. So you get the unit vector, and from once you get the unit vector, so each one of the quantities here, the X quantity, the Y quantity, and J, you would equate each one of those to your cos. Right? So you know what your cos is already. So you remember your cos alpha would have been your FR12 vector divided by the modulus of the FR12. Right? And so whatever you get for the ratio, you take the cos inverse of each one. That is for the X. and then you have the cos beta F1, 2, and that would be the x component, while this is the y component upon the magnitude, which is the 5 something. And you do the same thing for the gamma, all three. So the angle you get for alpha would have been 54.5, and the beta is 88.1, and gamma 144. All right, the F now. So I know a lot of persons challenged with this part. F, let me go back to the slide and find it. It says, can you also, what I'm looking at here, looking at the PDF. So the F here is just simply looking at the triangle and trying to identify the components of AD. So the tension in AB will result of all three forces pointing directly downwards. When it pointing directly, if the resultant is pointing directly downwards, that means all components in the horizontals are 0. That is the first thing to be established, right? So first thing, so all components are 0. So we're gonna go back. All right, so that is pretty easy. Everything else is 0 except it in the XY plane. Simple. And this week lecture, these things are gonna come out a little clearer because we're gonna get deep with it. Where is it now? All right, so let me take a page. All right. All right, so this is the. All right, so let me go for another page. I'm gonna take this diagram down. All right. There. So as I was explaining in the previous class, this part is not seen readily by a lot of students, especially if you don't have experience with 3D vectors. I'll try to spend a little time, just a little time, and explain it. All right. So you need some experience with 3D vector, and probably you would see this part readily. So what happens here? All right. So they are actually telling you that the resultant force, I'm going to use a different color marker. So the resultant force for all three, so this is F resultant 1 plus 2 plus 3. So all goes down here. The fact that that is happening, everything up here, so it will have, so you want coordinates up here. So the resultant, for the resultant, so the resultant 1, 2, right? Resultant force 1, 2. We found that before, right? And what was this value again? Let me see if I can recall it. I just wrote it. It was one of the last equation I wrote. It was 334.1 I plus 19.5 J. The space, and then the other one would have been minus 467.7 K. So that would have been the resultant force of 2. But I told you that when all three forces are going down, their overall resultant is just pointing down in the Z. Right? So in the Z, as a result, the resultant force is in the Z. So in the Z direction, it's not 0, but all the other components are 0. So I was showing the class the last time. I went through a series of things to try and explain it. So we said that what they really want is they want the tension in this line here. I think I want to go from A to D if I remember the question. Yeah, they want to go from A to D, but they don't have these components here to find it, and they don't have this one here. Those are the unknown, but they do know that the resultant, the sum of the resultant force. All right, it's now in a way that you can follow. If you have any question, you can ask. So when you sum all of the forces, come on, all the forces in the x direction, based on what happened. So sum all the forces in the x direction, you find that. So look, in order for the force to be going down, all the forces will have to, so the resultant force will incorporate x values of all the forces, y values, and the z values. So I'm going to write a statement there now, and I'm hoping that you're not confused when I write it. So you have FAB, right, x plus FACX plus FADX, right, really equals to 0, right? And you similarly have the sum of the forces in the y is going to be FAB y plus FACY plus FADY equal to 0. And then the sum of the forces in the z is going to be FABZ plus FACY plus Z. Sorry, this is Z. You have to concentrate with this one here, guys. Easy for you to mess it up. So typically that's what they are saying, right? So I want to make another statement which make sense now. So we are saying that the sum of the forces in the x, sum of the forces in the y. So we know that from the y, this one is not 0. This is equals to the resultant force, right? This is equal to the resultant force. For the z is not 0. It's going in the positive z. So it only have component in the positive z, right? So it don't have components. So it don't have components in the other, but so for the z, it's going straight down, right? So this will not have a component in the z. Now that will not have a component in the z. These are 0, right? But it's going straight down in this one. That's what you are told. Now, the fact that you are told that, you went ahead before and you did find the resultant of all these forces, didn't you? Which you have right over here. So we know that F1 plus F2 resultant force. Let me write that. So the resultant force, how did I write them before? I don't want to be writing them one way. And so resultant of 1 plus 2, or 1, 2 is equal to 334.1 I plus 19.5 J minus 467.3 K. So we know all of that. Yeah, that is what we were told. So from this, we know that these components are 0 in terms of the ZX axis. From that, we can relate now to say, we can make another statement and tell me if it makes sense to you. I think I'm running out of space. Let me just copy this, go down. I'm gonna pull it down. Tell you what, let me get everything. Let's stop that. Let's get when I take everything and we talk about it, because this is part that this week coming is going to be the week when we dive into some more of this. So look, that force, right? It tells you that we need AD, but for AD we don't have the X component of the A. We don't have the Y component. Now, I showed the class that each force will have component in the Y, in the sorry, in the Z, sorry, this is Z, in the Y, and in the X. Right. I also show them that this will have component or similarly in the X, Y, and the Z. This force over here will have component in Z, X, and in the Y. Right. So they will all have components there. So if you label them, you see them here. So if it's C, C is gonna have component in the X, Y, and the Z axis. Right? So it will have, this is Z, it will have components in the Y and the X. So see them here? These are labeled. For C, it is be 1, 2, 3. Those components. For AB, AB would have component in the X, Y, and the Z. Of course, we know that these two are 0. That is 0. Right? Right, so in other words, it have component in all of these directions. So all three forces will have component X. So this is typically how we do. We look for all of them and add them, right, all along here. So, right, so let me just take this out as 0. But these are typically, I can't even write on it, I forget that it is fixed. So those are components of it. And so, as a result of that now, I can say that the resultant force in the X direction, right? Because remember, when you sum all the forces in the X direction, which is what? Up here, the E equal to the resultant force. So it is going to be Rx, sum of the forces in Rx, plus F A dx, which is unknown. See it up there, F A dx is equal to 0. Because I know these, I know that one, you know. Don't I know it? I found it already. It was 300 and when I sum those two components, when I sum those two components in the X, I got this value here, 3, 3, 4, 1. And similar when I sum all the Y, I got this guy here. And when I sum and for the Y, the Z, I got that value. But I'm only interested in the X and Y component. So therefore, I can make this statement down here that I'm making. So so the sum of the forces in F of Y equals 0, which is imply that the formula of the forces for the Y plus F A D Y is equal to 0. This makes sense. So I know FRX. Don't I know that? Because I found it already up here. So let's put it in. It is 334.1, right? From the resultant force here. Plus FADX, which is unknown. So all three. So in the X direction, there's a force here. In the for D. And for C, there's a force here. For B, there's a force here. So for B, for AB, for the line AB, this is it. For what do you call AC? Here's AC line. See it here? This is the X. All of them and all of the lines will have a component X. Similarly, have a component in for in the Y, and they have a component in the Z. And so their resultant, the sum of all of them would have a resultant force as a result of that in each line. So in the X, you'll have a resultant force. In the Y, you have a resultant in the Z. In the Z, you know it already, but you don't know it in the X. But we found when you combine two of them, just two, the X and the Y, we got those values. Not the Z's, you know. We got those values. So we say that now is this, and this one is only unknown in the third line, right? Which is going to be equal to 0. The other one, for this line here now, it is going to be, these two are 19. So it is 19.5 plus FAD for the third line, which is unknown, ADY, right, which is equal to 0. Now, from this statement, you can find So this is implied is you can simply transpose a f a d. So you know for the for the x, it is really minus 334.1. And for the y, it is f a d y is similarly minus 19.5. And you notice they are most minus because they're over here in the quadrant. So this for the x, it is 19 for this side, negative, and for the y, it is so no, let me go. For the y it's 19, for the x it is negative minus 334. Right. But remember, so you have a triangle here. So what we have there is a triangle like this. This is 19.5, while this is 3, and they're all in the negative zone for that triangle. So this point is D. Right. So in order to go back to find this beautiful figure here, let me see if I can find something to highlight it. Which color is good there? Don't see a color that we have used. Well, this one. So this is a triangle that we are interested in, people. How much are you there? There? That triangle there. So that triangle there is really this. Let me see if I can draw it for you. So it is really this. The back line is really 90-degree falls. Right here. So it is this. Come on, where's the green? This is it. Look. So that back line is there. So we have that angle, which is, we give you this angle, it is what, 55? But we need to find this, so we need to find a line there, right? We need to find this line, which is unknown. Let me point the line that you don't know. This line on that triangle. This is 90-degree. This is A. Sorry, this is D, pardon me. And this is A in that triangle. Can you see the triangle I'm talking in green? Who don't see it? Talk to me. Straight up and be quick. Everybody see the triangle?
Yes, sir.
Yeah, man. So this is a line. See the line there? But we don't know that line, so we need to find it. So if we use Pythag because this is a right angle, and we use Pythag and we can find that side. That side when you use Pythagoras, what is value again? For Pythagoras, for that value, what was it again? I'm looking for the value. So for that value, you will typically get use Pythagoras, so the two of them, you get this value as 334.7. So this is 334.7. I need a block. All right. Now they said that they want, what did they say they want from you? They want the tension. We go. They want the tension in the line. Let's look back at it. So they say if the rope in the tension AD is to result in a resultant force of all three forces pointing directly downwards, what are the X and Y component of the tension in this third rope? Right, they say what is the X and Y component of the tension in the third rope? So we found the X and Y component, but we actually can't find the tension in the third rope. We don't find the tension in the third rope. So we find that now. We find it. So these are the tension in the, that was in the what? That was in the X and this is in the Y. So therefore we can find the tension from this. So tension, so what is that? That's a cos. So cos 55 is going to be equals to 334.7 divided by the tension. And simply all you do, right, you're just going to apply your trig. So tension is equals to 334.7 upon cos 55, sorry. All right, and so for that value, let me tell you what the tension is supposed to be. Did I work it out? So the tension is equals to 5 83.4. Right. All right. The next part of the question. This one is very crowded. You'll have to find another diagram. Do I have another one? And this one is less crowded. For the last part, just quickly walking you through this part here. This part here, it's a different page. Do I need a different page? Yeah, I need. Oh, this one is so big. All right, so for this one, what they're saying here, let me remind you what I want us to find. It says, so we found the tension in the third rope. All right, and so you have to determine magnitude of the tension in this third rope, which we found. So that was actually found 1 and 2. You have to determine the angle between F1 and F2. So it's a dot product now we are to use. How do you use a dot product? What did we have to use a dot product? We had found both of them in their Cartesian format. So we're gonna remind ourselves. So F1 and F2 in Cartesian. So we're gonna apply the dot product. Let's look at it. The dot product, what is F1 again? And F2. Trying to find them again. I'm gonna write them out. F1 was what now? 143.4 I plus 248.3 J. And then this is minus 200.7 K. The next one was 190.7 I minus 228.8 J minus 267.0 K. So those are pounds. All right, because this is 400. I can always put pounds to them. Those are pounds. All right. So now that you have the two forces, they said that you are to find this. They want this angle here. Theta, that angle. So it's simply dot product. The dot product says A dot B, vector A times vector B is equal to the modulus of A, the modulus of B cos theta. And so that is an easy, straightforward application. It means if you want to write the force down, so it's F1 vector times F2 vector is equal to the modulus 1 of F1 modulus of F2 because of the angle between them. Did we find the angle at any stage? No. So we can find the angle now. So we have the vectors. So how did we find F1 vector times F2 vector? So it is simply going to be 143.4 I times 190.7 I. You can actually put the i's them outside if you want. And I erase those, or my eraser is so big, then I get it smaller. Oh, great. Got it smaller. I know what happened. So basically what you could do, for clarity, what I'm actually saying, the I square is 1 plus, what's the next one now? It is going to be 248.3 J times minus 228.8. You could just put it in bracket and put the J square outside. And plus, you don't have to put the J square, guys. I'm just trying to show you from a teaching perspective the principle. You're really not going to have to put those things in, right? Because those would be too much. You would make mistake. So you just know that those goes and the K's goes. I just put in those just to kind of clarify. Those are 1, those are 1. So you don't need them. So these would give you a pretty chunky final answer. My notes didn't actually work them out that way, but those are the big values. And then now when you finish, So whatever value work there, somebody can work out that value and tell me. I think it's something like somebody said they got something. Somebody work out that value. The next step, it is going to be F1 modulus times F2 modulus. What are the modulus? We have them. It would be 350 times 400. All right, what was F1? F1 is 350 and that one is 400. Right, and those would give you a pretty nice value. Could I get those values, please? Could I get those values? Let me look for a calculator, please, because nobody talking to me.
So the answer would be
Hold on a second, please. Thank you for coming and grabbing a calculator if I can find one. Not seeing my calculator. 1 second, please. I need my calculator. All right, my calculator is out of space. Out of place. Oh, here you go. All right, so give me a value. What do you get for the first one?
for the modulus F1, F2, I got 140,000.
Can somebody confirm that one? What about the last one? The first one, the entire thing.
Sir, for the F1 times F2.
Yeah, yeah. For the ones that I did first section. The
Sir, I
second,
got 24,122.24.
yeah. Any more? Find what?
0.24.
Yeah, that sounds right. And that's a certain about the second one. Make sure the second one should be right because those are two numbers. And so when you get that, you just put that in your formula. So it would have been, so back in the formula, back to this, which is saying what now? Let me get a black writer. Those are the purpose. The black writer says F1 dot F2 is equal to the modulus of F1 modulus of F2 because of the angle between it. And so this one would have been 2, 4, 4, 2, 2, 4. This one is equals to 1, 4, 0, 0, 0, 0 cos theta. And then now you just transpose your cos. So cos will be equals to 2, 4, 1, 2, 2.24 divided by 1, 0, 0. And how much you get for that? So cos theta will be equals to, what is that? Punch it in, tell me answer. Where will you show you that?
Sir, I got 0.1723.
1723. Any other decimal?
0, 1.
All right.
So
Do
0.
the cos inverse of that and tell me what you get. And tell me if you let me get the answer and I know if it's correct.
So I got 80.07, but round up it would be 80.1, sir.
Very good, very good. So yeah. Very good. That is the answer. I just put in back the 2 here. Yeah, so that is the answer. So theta would have been the cos inverse of 0.1723. So that is equal to 80.1 degrees. All right, so that is simply that product, guys. The last part of the question is just using back the same formula here. Finding a line parallel to a line, or a line projected onto a line. And basically what we're saying here, so it's a line parallel to the line AC. How do you do that? You could simply say it is F1 times the unit vector of AC. So you could go that route. Or you could say F1 cos theta, because it's a projection and what? We have now find the line between them. So you have, what are the two lines we are dealing with? We are dealing with, this is A, and this was what? C, and then this was B. And we found the line, the angle, which is what? 80. So we could take many approach. You find, if you want, so this was what? F1, and this was F2. You could take many approaches. We know that this was what? What value was this again? 350. So, and then this one is 400. Was that it? 400.
Yes, sir. Yes, sir.
Yeah. So all we did, all you need to do to find out, so if you want a line, so if you want to get a line from F1 that is parallel to AC, it means that you need the unit vector of AC. But we don't need that. You know why? Because we have the angle between it, so you could use this other formula here. So it would have been just 350 times the cos 80.1. All right, and that would give you, I think it's 60 something, 60.3. Oh. All right, so you could do that, and that is getting a line parallel to it, or you could say you have projected F1 onto the line AC. You follow? All right, so that is projected. Another way, so if you want the perpendicular, I think the next part of the question, want the perpendicular, so F1 perpendicular to AC, that is parallel to AC. F1 parallel to AC is that. That F1 thing didn't write too well. We'll fix that. This is F1 parallel to AC. And if it's parallel, instead of going around it, so if you want F1 parallel to it, you just have to say sine 80.1 times F1 was what again? Let me write that properly. F1 was 350. So it's 350 and 350 pounds, all right, sine of the angle between them similarly, which is 80.1. Right, because essentially, guys, that's what it is, right? And it says the angle liable is 0 to 180. And so that would give you 4.8. Now you can go ahead and prove it, you know. You can find the unit vector for that line which you have and multiply it. Let's find, what's the unit vector for the line again? Didn't we find it? Let's find the unit vector for the line. Let's see if I can find it. Unit vector for the line AC. Let me search the note and see if I find it. AC unit vector. Where is it? I think this is it. So AC unit vector would have been 0.4767 I minus 0.5721 J minus 0.6674 K. So those are the unit vector for that. You could try F1 by it now. So what was F1? F1, so you could try it this way now. So it would have been F1. Where is it? So F1 times the unit vector. So that's so the difference with this one is that this is a vector one you have to do. This one is a vector, while this one is a scalar. Make sure you observe that. So if you're going to use this one, it says F1 parallel to AC is equals to F1 vector dot prime unit vector AC. It is two vector you're dotting now. So if you dot the two vector, you're like repeating the process before. Did we do it before? That's okay. No. Let's just no, we didn't do it. So it's F1 was what again? F1, F1, F1. I'm looking for F1. F1. Oh, so F1 would have been 143.4 I plus 248.3 J minus 200.72. Right. And then you dot it with the unit vector, which is going to be 0. I don't think I left enough space. 767 I minus 0.572 I J minus 0.6674. Run out of space. Well, I wrote too big before. Let's see if I can write that. It is minus 0.6674. 74 and then K. Right. So who want to do it now? So it's this one says 143.4 I times this one is going to be. And please work it out. I'm not working it out. I was writing them down. Right? So that one is I times I. That's one alone. Then you go J times J now. 248.3 times minus 0.5721. Was that really minus? Yeah. That's a J. And the K now would have been, the two of them are, let me see what is it. They are both minuses. So I'm going to put the 200 first. 0.7 minus times minus. You know that is going to give you a plus 674. Okay. Can somebody run through that and do the calculation, please? I'm tired, I can't do it. I'm just setting it out for you. And tell me if you get 344.8. All right, you should get that. You should get one scalar value.
Sir, I'm getting 344.4.
Yeah, half a little bit mean the decimal, but it's the same thing. You see that you get a scalar value?
Yes, sir.
Yeah, man. Same thing, but it's just you have to appreciate. So when you so when I use F1 modulus times the cosine. So in other words, the projection of the line is a scalar value times the cos of it. But sometimes you don't have that, so you have to go to the unit vector of the line that you want to project on, and then you can multiply it by its force. If you do the Cartesian multiplication, you get the value. If you just do the trigs, you get the same thing. All right. So that is it, folks. I recap the lecture on the tutorial. I'm gonna send you a detailed lecture though, which is on YouTube for you to, when I went through it in details. So all right. So I trust that the few of you who came out benefited. All right.
Sir,
Yes.
good night. You said you were going to send the previous tutorials after we finish them. Are you
Yes,
still
man.
going to do that?
Yes. I did.
Okay.
You have them already, you know. You didn't see them.
No, sir, but
And they are
thank you
open
then.
in Moodle. They are open in Moodle. I'm gonna open this one in Moodle and I'm gonna send it in WhatsApp. And I'm also gonna pull my YouTube video right now. Oh, let me stop recording. Pause recording.